I am Dr.S.SIVAKUMAR from S Engineering College, Department of Computer Science and Engineering, Associate Professor. Now we'll discuss some of the gate questions in computer architecture. Before going into that, we'll discuss the steps involved in execution of an instruction. The user writes the program and stores the program in the hard disk. The first step involved in execution program is compiling. When user compiles a program, the entire program will be stored in memory, and then the processor reads one by one and executes it and convert it into machine understandable language. So now we'll discuss the step number one is the absolute loader loads the program into memory. In the wherever this free space available in memory. Suppose the program is loaded in this location, starting from 7000 to 7020. So in this part, the program will be loaded in memory. This is done by the absolute loader. So absolute loader will load this OS. The relocatable loader will load this program into memory wherever the free space available in memory. Next, this instruction will be given to the operating system where it has been loaded. The starting address is known to the operating system. This operating system knows the starting address of the program. This address has been transferred to program counter. So program counter knows the address where the job one has been loaded in memory. Suppose the program counter address is 7000. Second step is involved is this address will be transferred to MAR in, that is memory address register in. And then read signal, next step is read signal is generated to read this particular memory location, that is 7000. During reading, CPU has to wait for some time. The next step is WFMC, that is wait for memory function to complete. So this is a delay so that the processor will read the entire data that is present in 7000. After reading, the data will be transferred to MDR in, memory data register in. From memory data register in, the data will be transferred to IR register, that is instruction register, where the decoding has been done in IR register and the control signals are generated. In IR register. So the entire this is the first step for the execution of an instruction. Similarly, second step, third step, this step has to be followed. So now we will see the gate questions. Number one is consider a 3-stage pipeline processor having delays of 10 nanoseconds, 20 nanoseconds and 14 nanoseconds for the first, second and third stages respectively. Assume there are no other delays and the processor does not suffer from any other pipeline hazard. Also assume that one instruction is fetched every cycle. We have to find the total execution time for executing 100 instructions like this. So answer for this is C. The pipeline cycle time is determined by the stage with the maximum delay, which is 10 nanoseconds. The total execution time for executing is 100 instructions calculated as the number of stages, that is total number of stages, nothing but 3 plus 100, that is 3 plus 100 minus 1 plus number of instruction minus 1 into pipeline cycle time. So when you substitute all this value, we will get 2040 nanoseconds. A 5-stage pipeline has stage delays of 150 nanoseconds and 120 nanoseconds and 150, 160 and 140 nanoseconds. The register used between the pipeline stages have a delay of 10 nanoseconds each. The total time of executing 100 independent instructions on this pipeline starting with an empty pipeline is 17,000 seconds. Explanation for this is the pipeline cycle time is determined by the stages with the maximum delay plus the registered delay. So the maximum delay is 150 and 120 and then 150 and 160, 140 plus 10 nanoseconds. Total will get 170 nanoseconds. The total execution time is calculated as total number of stages is 5 into 100 minus 1 into number of instructions is 170 nanoseconds, that is equal to 104 into 170 nanoseconds is 17,680 nanoseconds. However, consider the option the closest is 17,000. So we have considered this option C is the correct answer. Third one is consider the pipeline processor with the 5-stage instruction fetch, decode instruction and then execute, memory access and write back. If the instruction fetch, instruction decode, execute and write back stages have 1 clock cycle time each to complete and the memory stage takes 2 clock cycle to complete. Assume that there are no pipeline stalls. The number of clock cycle required to complete the execution of 10 independent instruction is, that is here the pipeline has 5 stages but the memory stage takes only 2 cycles, effectively making 6-stage pipeline. The time to fill the pipeline is equal to the number of stages, that is given as 6 cycles. After the pipeline is filled with each subsequent instruction to complete 1 cycle, therefore the total number of cycles required is, that is the time to fill pipeline plus the number of instruction minus 1, that is 6 into 6 plus 10 minus 1, that is equal to 15 cycles. Consider the pipeline processor with 5-stage pipeline. The instruction fetch, instruction decode, execute, memory access and write back. The instruction fetch, instruction decode, execute and write back stages take 1 clock cycle each to complete and memory stage takes 2 clock cycle to complete. Assume that there are no pipeline stall. The number of clock cycle required to complete the execution 10 independent instruction is, that is answer is B, that is 15. Since the pipeline has 5 stages but the memory stage takes 2 cycles to making a 6-stage pipeline, the time filled pipeline is equal to the number of stages, that is 6 cycles. After the pipeline is filled, each subsequent instruction complete in 1 cycle. Therefore the total number of cycles required is time to fill pipeline plus number of instruction minus 1, that is 6 plus 10 minus 1, that is 15 cycles. Next question is, consider a 5-stage pipeline processor with the following stages, that is instruction fetch, instruction decode, execute, memory access and register write back. Which of the following statement about forwarding is correct? Option A, in a pipeline execution, forwarding means the result from a source stage of an earlier instruction is passed on to the destination stage of a later instruction. In forwarding, the data from the output of the memory stage can be passed on to the input of the execute stage of the next instruction. Third one is forwarding cannot prevent all pipeline stall. Fourth one is forwarding does not require any extra hardware to retrieve the data for the pipeline stages. The answer for this is B and C. The correct answer, the forwarding allows data from the output of the memory stage to be passed to the input of the execution stage of the next instruction to resolve the data hazards. And second answer is C also correct. While forwarding can solve certain data hazards, it cannot prevent all pipeline stalls such as caused by control hazards or certain data dependencies. Thank you. We'll see you in the next section.